Okay, so continuing with our discussion of concavity, let's make these things a bit more official. So here's what we're going to do. We want to be able to find. Well, actually, we need to start with the relevant conditions. So let's suppose. Sorry about that. Let's suppose that we have a function and we need, what do we need? We need that f double prime of x exists over an open interval I. Okay, so we have the second derivative exists. Then in order to find where f is concave up, down, and inflection points, do the following. Now essentially what we're going to do here is we're going to use the same test that we used for critical points, but we're going to shift it down to the second derivative. Okay, so step number one is we need to find the domain of the function, because this is always going to be relevant, because if you have kind of a weird domain where you have points that are excluded, you need to be aware if one of your supposed inflection points also is not in the domain, in which case you have to exclude it. So that's always going to be relevant. So anyway, so first thing, to find the domain of the function. Second thing is to calculate both f prime of x and f double prime of x. So the first and the second derivatives. Third thing is, and this is really we're basically finding the critical points of f prime, but we need to calculate and find the values x equals c, where f prime of c, I made a mistake, f double prime, where f double prime of c equals 0, or f double prime at c is d and e. It does not exist. So those are like the critical point. I don't want to use this word too much, but the critical points of the derivative. So whereas before we were finding the critical points of the original function. So yeah. Now with these numbers that you get in step 3, so these are possible potential inflection points. And just as, how do we determine whether something was actually an extreme value? Well, we evaluated the sign of the derivative, and then that told us if the sign changed from, as we passed on one side of that point to the other side, then we actually had an extreme value of some kind. It's the same thing here, but using the second derivative. So we're going to kind of cut up the domain, or divide the domain, cut up the domain into intervals Oh, you know what? I almost forgot. Before we do that, sorry, we need to check something. We need to check that your possible inflection points are actually in the domain of the function. So check that f of c is defined. That's important because you could, as I was saying before, you might find a potential inflection point, but that wasn't even in the domain of the function, in which case you have to exclude it. Okay, so do that. All right, now we can move on to the next step. So I guess that would put us at number 5. So step 5, break up the domain of f using the possible or potential inflection point list that you got. Okay, so let's say that we got 1, it was x equals c. So then if your let's say if your domain is, just for example, if your domain is the interval a to b, the open interval, then you would do a to c and c to b. And then so that would be breaking up our domain. Now, of course, it may be more complicated than this, but this is just for illustration. And then just like we did before for the first derivative, now we're going to look at the sign of the second derivative. So this is, I guess, step number 6. We're going to evaluate the sign of f double prime of x at test points within each subinterval. Okay, and what we're looking for is for if f prime of x is greater than 0, that means what? It means that f is concave up, and if f double prime of x is less than 0, that means f is concave down. And if furthermore, if you change concavity, if you go if you go from concave up to concave down and vice versa, then you have an actual inflection point, right? So you choose a number, choose the test value in here, you choose a test value in here, and then you evaluate the second derivative. And so if you got, for example, if you got that the second derivative was positive over here and negative over here, then you'd know that f was concave up and concave down, in which case this value x equals c is an inflection point. Now, we don't really distinguish between the types of, if for an inflection point, it's just an inflection point. There's only one kind, so it's not concave up to down inflection points or anything like that. There's just one type of inflection point. But if it doesn't change sign, so in other words, if this is increasing and then still increasing, then x equals c is not an inflection point. Okay. Okay. So that, and with all this information, now we can figure out where are the intervals, what are the intervals where a function is concave up, what are the intervals where a function is concave down, what are the inflection points. Then we could go back and do our other test from the first derivative and determine where the function's increasing, decreasing, and what are the maxima and minima. And then if you kind of put these two tests together, you can figure out where a function is increasing and concave up or increasing and concave down, and so on and so forth, and kind of construct a pretty good picture of the function. Although it can get a bit confusing, but that's kind of what we're aiming at. Not to be confusing, but we're aiming at getting a good picture. Okay, so there is a related topic. And I think sometimes people get confused because there's the name of this other thing. So there's another test which is called the second derivative test. Okay. And you might think, oh, weren't we just doing the second derivative test? Well, unfortunately, what we were just doing is not strictly called the second derivative test, although it used the second derivative. The second derivative test is certainly related, but it is different. So what is it? The second derivative test is actually another method. It's related, so it's another related method that uses the second derivative to give you, to tell you, or to find the extreme values of the function. Maxes and mins. Maxes and mins. So how does that, just in case you're fail to see the difference here, this is about extreme values. What we were just talking about was about finding inflection points in concavity. So this is, the second derivative test it basically does the same thing as the first derivative test. So note that the first derivative test also does this. Finds maxes and mins. So you may wonder, why do we need another way to do this? Well, sometimes the second derivative test is easier. Okay, but just keep this separated in your mind, that the second derivative test is not strictly about finding intervals of concavity and inflection points. If you want to find intervals of concavity and inflection points, then you use this, I didn't really give it a name, but it's, let's call it a concavity test. Okay, so, you know, kind of unfortunate terminology, but that's what we're stuck with. So now, of course, I haven't actually told you what the second derivative test is yet, so I guess I'd better do that. Okay, so let's talk about the second derivative test. And as you see here, I said this is about maximums and minimums, not about inflection points. So we've got some conditions. So let's say we have a function f. So if f has a continuous second derivative on an open interval, so there's kind of a lot of conditions, but an open interval AB that contains a critical point of f, call that critical point C. And furthermore, it needs to be a particular kind of critical point. It needs to be a kind of critical point where the derivative is 0, not a D and E. So this does not work if it's a D and E. That doesn't work in that case, okay? But if all of this stuff is true, okay, so if all of that is true, and then we evaluate the following. So if we evaluate f double prime at the critical point and it's positive, then f has a relative minimum. So it's kind of the opposite of what you might have thought. Has a relative minimum. That's number one. Number two, if f double prime at C is negative, then f has a relative maximum. And finally, if f double prime at C is 0, then it's inconclusive. Okay, so that is the second derivative test for extrema, for relative extrema, minimums and maximums. So we get a critical point, and then we put that critical point into the second derivative and evaluate it, and then that tells us something about the original function. Okay, so now we need to talk about how to use all these things, and we will do that in the next video or lecture.